Ladies and gentlemen, this is Murad Rassam from Information Assurance and Security Research Group, Faculty of Computing, University of Technology, Malaysia. In the next 5 minutes, I would like to show you our new contribution, which is accepted for publication in knowledge-based system journals and titled Adaptive and Online Anomaly Detection Models for Wireless Sensor Systems. The quality of data in sensor networks is very important for making the right decisions. However, this quality is affected by some reasons, which are node software or hardware failures, reading errors, unusual events, or malicious attacks. Therefore, we need such an efficient and effective real-time detection methods that are able to detect these kinds of anomalies and keep a higher level of data quality. Variety of anomaly detection methods have been proposed for sensor networks. However, they have their own drawbacks in terms of efficiency and effectiveness. For example, they incur additional communication overhead or high computational complexity that may drain the limited resources of sensor nodes. In this paper, we show how the unsupervised principal component classifier can be adopted as a one-class principal component classifier, which is suitable for anomaly detection in sensor measurements because there is no ground truth labeled data. Therefore, we proposed a new efficient and online anomaly detection model, namely BCCAD, which is principal component classifier based anomaly detection. After that, we enhanced the BCCAD model by incorporating a lightweight incremental learning method in order to track the data change in dynamic environments. We tested our proposed model using the Inter-Berkeley Research Lab dataset, and we used the accuracy, detection rate, false negative rate as evaluation measures to compare our proposed models with some existing models. In this figure, we show how the proposed BCCAD model outperforms the existing hyperplan one-class support vector machine and quarter sphere one-class support vector machine in all performance measures. We also tested the proposed models in terms of effectiveness using a dynamic environmental datasets, and we found that the proposed BCCAD model incurs some false positive rates. Therefore, we propose an adaptive version of the BCCA model called Adaptive BCCAD model. The adaptive model, as we see in the results, successfully reduced the false positive rates to 0 in most circumstances, in compared to the discrete wavelet transform in combining with one-class support vector machine or in combining with self-organizing map. We found that our proposed models, which are the BCCAD model or the adaptive BCCAD model, has a superiority in performance in compared to these two models for the dynamic data. In terms of efficiency, we found that the proposed models have the lowest computational complexity compared to the existing models. We see that the proposed BCCAD model incurs O order of n, where n is the number of observed variables. However, when we use the adaptive model, we need to add m to the computational complexity, where m is the number of observations used to retrain the model to cope with the dynamic change in the environment. Thanks for your attention.